demonstration. The first talk is Santosh Vempala, and you can talk about ODEs.
I'll take 30 seconds to make sure my MATLAB is starting. Oh, it's okay. Yeah, not on my screen. But thanks. Believe it or not, this is about randomized numerical linear algebra, and you don't have to take my word for it. You'll see in a few seconds. But the topic is ordinary differential equations. So just to remind you, if it's been a while, and I'm certainly no expert on this topic. This summarizes almost everything I know about them. But I think it's okay. So here is the first order one. You want to figure out the evolution of this this variable x. It starts at some v, and you know, let's say only its derivative, time derivative, how it's evolving in time, and in some interval. So this is what you'd like to do. This function is reasonably nice, so at least it's Lipschitz, and that's it. This is the problem. Solve for it, but it's multidimensional, right? So this is a first order ODE because you only took the first derivative. Second order ODE would be your second derivative depends on first derivative and the point you're at and time, and you know initial conditions for both the point and the first derivative. And again, you want to solve up to some time window. And then, of course, there's a kth order. So kth order, right? Yeah. Great. So it's a family of problems. Now, why? Okay, so sorry, why not? Yeah, it's Thursday afternoon last week. Do whatever you want. Yeah, why not? Right, good. Many reasons, most of which I don't know. But one thing I do know is it, is pretty pressing evidence that your brain is doing this all the time, if only to balance neurons that are excitatory and inhibitory and reach this balance. Okay, but optimization. I mean, the very successful interior point method is a single ordinary differential equation that you have to discretize to get an algorithm out of. Okay. But the focus application for this talk, just to is sampling high-dimensional distributions, but not all. Specific ones that seem to be of particular interest, such as sampling from the logistic loss function. And I'll if you don't know this, I'll mention it. Well, here. So it's a sum of one-dimensional functions applied to inner products here, and you'd like to sample. So these are all convex. The whole thing is convex, and you'd like to sample according to this log concave density. Okay, this might be the probability of a model, and you're sampling according to loss. In this, if you pick the phi to be, for example, this what is this called? From the sigmoid, sorry? Logistic loss, then you would get the KL divergence is what you're sampling from, right? Good. Right, you just mentioned that. But more generally, maybe you want to sample according to some function here. We know how to do it according to convex functions. We know how to do according to strongly convex functions. We know how to do according to smooth strongly convex functions. These are implications. But the point is that hopefully things are getting faster and faster and faster, etc. Right? And so all of these classes are of interest, not just because you want to do it in polynomial time, but maybe you want to do really fast. Maybe this is what actually shows up in practice, and so on. Okay, so here's one approach to doing this. Let's think of sampling as a continuous process. Diffusion, it's high-dimensional sampling. So look at some continuous process which at the end of the day reaches the density you'd like to see. So for example, this is one way you could do it. If you want to sample according to the density proportionality to the minus f, you can make a change at x. This is a point in n-dimensional space according to the gradient, negative of the gradient, and this is just an infinitesimal Gaussian, a Brownian motion there. The scaling factor is important if you want to get exactly this. So you could do this, and then it's a sort of a simple application of a standard theorem relating this to its limiting distribution to show that this is the distribution to reach. Okay. Now, this this, in fact, the convergence here for strongly log concave functions has no dependence on the dimension. It just depends on the smoothness parameters of the function. We'll see one of these proofs. But when you discretize, if you want an actual algorithm, of course, you have to discretize. Right? And simplest way to discretize might be, let's apply a not infinitesimal here, but instead of xt, let's look at xt plus a small h. And then that might mean that you do a gradient at the current point times h. And then here you pick a Gaussian whose variance is h. Okay? So that would be one natural way to do it.
These are independent Gaussians, right?
Sorry? Every step, yes. Yeah, it's a Brownian motion, so it's completely, yeah. Right. So when you discretize, you pick Gaussians of finite variance, but independent. Now, unfortunately, if you discretize in time with any sort of step size, it actually converges to a slightly different distribution. Close, depending on how small your step size is, but different. And there are variants to fix this or to make it faster. I won't discuss all of them, but this is there's a number of interesting papers on this topic. I'll mention some of them. Here is one particular approach to do this, which doesn't suffer from this problem that the discretization gives you a different distribution. Namely, it's called Hamiltonian Monte Carlo. And the idea is the following. Hamiltonian is a function of both the current position and its velocity, so to speak. And these dynamics, which I'll put up, let me put up right now, they preserve this Hamiltonian. So the change in the position is the gradient with respect to the velocity, and the change in the velocity is the negative with respect to this. So you can check that as you evolve these, the h itself will be maintained. Okay. Now this suggests a process, which is the following. At a current point x, we're going to pick a random velocity according to some local distribution. Throughout this talk, this will be just a Gaussian, standard Gaussian. So we're picking a random Gaussian direction. And then that direction defines a curve. And that defines where you'll go. The starting velocity defines where you'll go. You follow that for some discrete time. Okay. That's it. Repeat. So this Hamiltonian defines a curve that maintains some function which I haven't defined yet. We'll define a function because we need to have a goal. What's the end result we want out of this? Sampling from some density. So we can do this very generally. The same slide. But now, if you pick h to be something like this, think of g as just identity for this talk, but you can actually make it more general. If g is just identity, this is just the square of the velocity. It's sort of energy, and that's the function. And this is a constant, so this term just drops out when g is identity. So we're saying set the Hamiltonian to be the function plus, you could set it to half of v squared in the standard way. And then look at the derivatives. The derivative of x is just the velocity. dx by dt is just v. This is half v squared. You get v, excuse me. Do you mind if I take this now? G in general is, so at each point you don't have to sample from the same Gaussian. You have the flexibility of defining Gaussian depending on the local point. And one way to do it would be to have a local metric. For example, the Hessian of some convex function.
Okay. So you select the G basically.
Yeah, but right now, yes, it's prefixed. But for getting at what I'm going to do, and maybe I should have done that, let's just think of G as identity.
Okay.
Could you say time minus delta?
Yeah. Okay. You can go backwards, indeed. So yeah, so you can evolve, in either direction. So the nice thing about this is that, yeah, it's completely symmetric. And unlike almost any other process that's natural and candidate to be efficient, it doesn't require a rejection step to get your right distribution, even though it's discrete time. Okay, so this is the focus process I have in mind here. But note, of course, that we have to solve a differential equation to make a step. Right? So I have a current x and a current v, and after time delta, I want to know where will this x in x be. The v I'm going to repick, so it doesn't matter. Okay, so here are some representative guarantees for sampling. So if we take the completely general log concave setting, then there are discrete methods. that take roughly cubic in the dimension per point. Okay. If you want to do uniform in a polytope, you can do that with Hamiltonian Monte Carlo. And actually, for a polytope with m facets, you get this bound which is sub-quadratic, which turns out to be impossible for these methods. There is some evidence of a win for this method. I mentioned other diffusion methods, which we have to do some correction for, but nevertheless, they work under stronger assumptions, so strongly log concave, and strongly log concave with further assumptions. You get even better dependence on the dimensions, square root n and n to the 1/4 even. And this kappa here is a condition number. So it measures the local smoothness. Roughly speaking, you take the Hessian, or at least this suffices, and look at the maximum eigenvalue and the minimum eigenvalue and the ratio of them. Right? So the global ratio, maximum ratio of largest to smallest eigenvalue. So that's the condition number kappa here. So this result, I believe, is all the authors are here in Berkeley. This is Mangubi and Vishnoi. This is Mangubi and Smith. And I haven't put this up here for the following reason. The number of steps. So there's an additional, the assumption from going from here to here is that besides being strongly log concave, it's also smooth. So you also have all the derivatives, not just the first two. Is that the number of steps here abstractly depends only on the condition number as kappa squared. It doesn't even depend on dimension. But unfortunately, implementing each step has a penalty with dimension, and there's a various trade-offs here, so I'm not putting that for now. Okay. Okay. So before we go back to the ODE, I want to sort of show you how the ODEs are connected to even the analysis of these methods. Just sort of a precursor to the main part of the talk, and how the condition numbers come into the picture. So let's say we start with a function f, convex, and moreover, it's strongly convex in this sense. It has lower bounds and upper bounds on the Hessian eigenvalues. Then, what we can show is that for time up to, this is a number that depends on these condition numbers, right? So if they are constants, this is up to some constant time. If you start out at points x and y, and just run this process using the same directions at each time. Okay? So you take two copies of the process, x and y. You're starting at two different locations, that's all it means. But every time when you pick the same Gaussian vector for both of them, can you guess what will eventually happen? They'll meet. Because of the strong log concavity, they will actually meet. Okay, and the question is how fast. And now this already allows you to prove that things must mix fast, because pretend one of them is already random and the other one is arbitrary. And over time, they're getting together and actually coupling to become the same. So the point that was arbitrary became random. The question is how fast did this happen? So the trivial coupling of just identity, use the same direction, works because the gradient of the function is helping you go to the same place. And it's strongly log concave, so the gradients are kind of pointing you in the same global, to the same global point, no matter where you start. And that's enough to beat the noise and still get a distribution. So the contraction bound here is 1 minus this lower bound on the eigenvalues times the time squared. And so if you set this time to the largest possible, which would be the biggest step you can take so that you get the most contraction by solving a single ODE, for that setting, you can check. It's m over m to the 3/2, which means that the mixing rate is kappa to the 3/2, which improves a little bit on the previous best kappa squared. Kappa is the best possible, and not entirely clear whether we can do better than 3/2 or not. So here is one sort of straightforward open problem. This process or any process, can you get it to do mix in just kappa?
So xt is evolving according to the Hamiltonian dynamics?
Yes. Yes. Exactly, yeah.
So this lower condition is the one that is the Becquerel-Emery criterion. The lower bound on the
Yes.
Hessian is a Becquerel-Emery criterion for the log concave density to satisfy log so below inequality. But this is connected to the contraction rates for the infinitesimal semigroup generated by something else. Is there a relationship between this and the Hamiltonian dynamics, or?
So what I do know that's related to what you're asking is that for the Langevin dynamics, it's sufficient to have a log-Sobolev inequality to prove convergence, at least for the continuous process. Right. Yeah. Here, yeah, we're doing a direct coupling. Just applying the contraction here. Yeah. Certainly, this satisfies a log-Sobolev inequality. We're not using it directly. Yeah. Right. As far as I know, that process is still at kappa square, for what it's worth. So, yeah. Okay. So, why does this contraction happen? Right. So, this is one step. So, this just solving these paths. I guess I should draw something. These paths are you're starting somewhere, and there's a gradient pointing in some sense towards a global optimum, and so these paths are somehow bringing you closer to each other. That's the game. So proof has to analyze this differential equation, right? This is just the same thing that for the Hamiltonian Monte Carlo. Remember, the Hamiltonian Monte Carlo just said that the derivative of the current point is the velocity, and the derivative of the velocity is minus the gradient. Maybe I should write that here since it keeps coming out. Right? This is how you're starting, and then the velocity itself, which will keep changing. So it's the second derivative of the position. Will be the negative gradient of the function. That's the dynamics. Yes.
So a basic question, right? So the fact that you're going towards the gradient can only give you sampling or mixing if it's strongly convex. In some sense, if the function is uniformly spread out, you will get nowhere by.
That's right.
Right, okay.
So, for example, if you were trying to uniform in a polytope or any function that's not strongly convex, this proof method, yeah, that's right. Yeah. The coupling simply won't. Okay. Yeah. So one of the results I put up there was uniform in a polytope.
Right.
Where that has to use it doesn't use coupling. It uses a conductance proof. Shows that the expansion is large and so on. Okay. Yeah. Okay, so we already discussed this. We're planning to couple, and then that's how we get together. So let's look at this quantity between the two processes y and x. So these are just two copies. I mean, two different points at which you're starting. And the idea of the coupling is we pick the same velocity. Fine. Look at this difference, and we want to see how this evolves over time. So it starts at something at t equal to 0. We want to see where this goes. Okay. So by the definition of the process, the second derivative of this is the difference of these derivatives. That's just the difference in the gradients. Okay, but at every time t, right? That's the. So we want to know how this differential equation really evolves to show that its solution over time decreases in norm. So just rewriting this in terms of the Hessian, and I've parameterized to make this 0, 1. That's why I have this et coming out here. Let me call this quantity here, which is like an average of the Hessian on the line from xt to yt. That's all it is. On the line from xt to yt, we're averaging the Hessian. Okay, in this direction. Right. So that's what we have now. And yeah, the solution to this should be this integral. I've just integrated twice on both sides. Right. Here for this term, if you have not done it before, after you integrate twice, you have to switch the integrals to get the t minus s out. Okay. And then, okay, so far so good. And so then just take norms, and you see that the bound on the norm of the Hessian will be useful. And that's all I've done here. Now, this here is a one-dimensional inequality, right? Integral inequality, but it's one-dimensional. So you can say very generally that if you have any such one-dimensional inequality, v of t at most beta plus gamma times similar expression, right? T minus s times v of s, where beta and gamma are non-negative, then in fact the general solution for this is that it's at most the beta times the hyperbolic cosine of square root gamma t. Okay, it's like I guess an exercise in differential equations. But of course you can substitute and check. Okay, so using this, it tells you that this quantity here, just applying the lemma, beta is the initial norm, gamma is the Hessian's largest eigenvalue, you get some, and for t not too large, you get a bound on the length. So what this is saying is that this distance cannot become too big. It could grow, but it cannot become much bigger than what it starts at, up to this time interval. And in fact, once you have this bound on this distance, upper bound, it also gives you a lower bound, right? Because I can put it back here and say that I can't be subtracting for every step of the way, and therefore I can't be subtracting it too much either. So you get the bound on both sides. It stays up to this time between 1.2 and 0.8. Okay, it doesn't change much. Now this sounds a little counterintuitive to what we want to show. We want to show it shrinks, right? We're saying it doesn't go crazy. But that's the problem with these proofs. If it goes crazy, then you can't prove anything. Here it's staying controlled. So in this region, we hope to make progress. We should be making progress because everything here is pointing in the right direction. There's a negative sign, hits the Hessian, positive definite, and so on. So using this bound, we can actually argue that the squared length of this distance compared to the initial contracts at this rate, and then just use the... Now the point is that because you know it's strongly log concave, this quadratic form here has a lower bound, and that gives you a minimum contraction. I haven't shown you how this inequality is derived, but the basic idea is to split this vector ET into the coordinate along the line joining the 2 points and the orthogonal part, and you make progress in the line joining the two. Okay, so that's what gives you this bound. Okay, so that was motivation for why we want to do this kind of ODE, both in analysis and in algorithm. Now there are many, this is a huge literature. I think it's about comparable to randomized numerical linear algebra for matrices and solving linear systems and so on. There are many books. It's rich field, like numerical algorithms, closely related also, as you'll see, and as I'm discovering. And the classical results, are about uniqueness, about convergence, no matter where you start and for how long, very general and lots of really clean things. Our goal here is, we want algorithmic guarantees. So I want fast and non-asymptotic guarantees, right? So this will, by that I mean, I want a solution of error epsilon in time no more than some function of epsilon. And regardless of where you start, you can't tell me, if you start close enough, it'll work. No. Just give me a starting point as part of the algorithm. Okay, so back to first order ODE. So here, now we're at a completely general problem. You can forget it if you don't like sampling. I can't imagine why, but forget about it. Here is a problem to solve. How would you solve this? Right? It's multidimensional, but yeah. Okay, so you just integrate both sides, right? So integrate both sides, okay? Right? Integrate both sides. So we know what x0 is, and I just wrote down an integral there. So what should we do next? So it's very much like solving linear systems, right? It's an iteration where you just start with some trivial solution like the right-hand side, and then you keep operating on the residual. That's the plan. We have to figure out what the right operator is. It's not my plan. This is the plan of the field, and it works really well in many situations. So let's think of this operator tau, which is basically mapping these. Think of x itself as a function. At every time, x is a function. It's telling you what the values are, the high-dimensional values are. So it's mapping functions to functions. Right? It's modifying this function in the next step. The next x is a function of the previous x. Now, That means that what we're really solving at the end of the day, if you solve it, is x equals tau of x. So now modifying it doesn't change anything. It's a fixed point of this. Now, by very general considerations, this Banach fixed point theorem, it's enough if this operator tau, this t is tau, is a contraction. It will exist and it will be unique and everything will be nice. So we need the Lipschitz constant to be less than 1. And here Lipschitz constant is just the Lipschitz constant of f, because that's constant and this is a 0, 1. So if the Lipschitz constant is less than 1, it constant. But you have some ODE. Why should this Lipschitz constant be less than 1? Maybe it's Lipschitz, but not less than 1. Of course, this is dealt with in the literature. What if it's L Lipschitz for some L? And this type of theorem is called the Picard-Lindelof theorem. And it just says, imagine operating this operator not once, but j times. Okay, in one step, you couldn't get a contraction perhaps, but let's look at j times. And now, basically, I'm defining this norm as the maximum over this time interval that you're looking at. And if the Lipschitz constant for one step, right, for the function itself was L, I should have L somewhere, yeah, L Lipschitz, then for this operator applied j times, it's LT to the j divided by j factorial, where t is the time interval you're going for. So now, by making j high enough, you can make this less than 1, which literally means, but just by composing, eventually you'll contract. Yeah, and there is a fixed point. So all you need is the function's Lipschitz. If you haven't seen a course in differential equations before, here is a proof of uniqueness and existence and all that. Okay, I was going to prove it, but I think I won't have time. But here's the next question. Okay, so this is the general theorem that there exists this, but how do you turn this into an algorithm? Yes, fine, yeah, good. So the natural iteration would be to do exactly what we did, right? The most general fixed point algorithm is just apply the operator. The trouble is, x is a function here. How are we going to represent it? It's this entire interval, right? How do we represent it? We can do separately for each coordinate. That's not a problem. So the idea is, functions also have bases. Okay, of course, it could be infinite. But let's hope that the solution to this ODE is close to some finite dimensional basis. So you could pick a polynomial basis or a Fourier basis or some nice basis. But in that basis of functions, that your solution to your ODE is close to that. Okay, so for example, if you had this basis and you pick some evaluation points, so now the idea is instead of maintaining the entire function, you're just going to maintain its values at a small set of points. So if you picked a polynomial basis, for example, you just need to evaluate it as many points as the degree and keep those around for all the basis functions. So that's the plan, and you can always pick an orthogonal basis, and then this is just saying that every function, this is the basis, every function can be written like this because I picked an orthogonal basis. And now this leads us to the method. That's the natural iteration. So how are we implementing it? Picking an orthogonal basis, picking nice points. For the polynomial basis, we can use this Lagrange basis. You can check that this basis satisfies this. At these points Ci, it's 1, and otherwise it's 0. J. And in fact, it has a sort of bounded norm. It's not something that has very huge coefficients. Great. Now, if indeed the solution to your ODE is approximable by a low degree polynomial, or degree of some degree d, degree k, then you can write it again in terms of this basis, and then the derivative by definition of ODE is this function. And now you're computing only at the points, the test points. There's your iteration. That's the algorithm. So we're going to keep computing the function at these test points. This is the collocation method. It's one of many methods. So just want to point out that it's a super fast method because you're just doing basically a matrix product, but this is a pre-computed matrix of coefficients. Okay. So using this, I won't have time to mention it later, but I was going to tell you that this is highly parallel also. The complexity is just the number of iterations, parallelizable. Okay, so this is the guarantee you get. If you started with that first order ODE, and you assume that there was a good polynomial approximation using a basis of size d, then if you started with any L Lipschitz function, the collocation algorithm finds you a solution obviously a polynomial, because that's what it's finding, whose error is as small epsilon as you want. And the running time, the number of iterations is only log 1 over epsilon. That's it, log 1 over epsilon. Each iteration has d function evaluations where d was the degree of the polynomial, the number of basis functions. So that's it. So going back to HMC, this was the algorithm for Hamiltonian Monte Carlo. And now we need to show why should these ODEs have low degree solutions. Right? Otherwise the whole thing, or Fourier basis, why should they have only a few Fourier coefficients? We need to prove that, otherwise it's all up in the air again. So to do this, it depends on the properties of f. We have to develop an approach which generalizes this notion of Cauchy estimates. Therefore, one variable functions, I should stop in a minute. We can estimate kth derivatives if you know that the function is complex differentiable in a neighborhood. That gives you a bound on all its derivatives in a small neighborhood. Now, why are derivatives useful? Because then you can look at the Taylor series, and if your derivatives are decreasing fast enough, then you truncate. That's the plan. So, yeah. But how do you do it for high-dimensional functions? We can develop a calculus to do these inequalities. Basically, if you define the norm of kth directional derivatives, then you get these calculus rules that say, for example, if a set of inequalities are true for functions capital F and small f, then it's true for the sum, it's true for the product, and so on. And using these, if you wanted to bound this general ODE here, I put second order because that's what happens in HMC, you can bound the Lipschitzness in terms of one-dimensional functions which satisfy one-dimensional ODEs. So the problem of bounding the Lipschitz constants of these general high-dimensional functions becomes one of problem bounding it for one-dimensional functions. And indeed, in our application, we just at the end of the day have to bound the values for this function, a over 1 minus ct, and that's enough to get all the bounds. Okay, for logistic loss, let me just put up the result. Here's what you get. This is for general functions phi, but for the log one, you get linear in n and kappa to the 1.5. That's the total time plus O tilde 1 function evaluations. That's a single log. So it's actually truly linear times the condition number to the 1.5. Collocation, I mentioned, it's highly parallelizable and you can extend it in other ways. Lots of open problems here. Complexity of ODE. Is, for example, order L possible? I meant little o. Is order L possible? Yeah, we have 3 halves. Is better than L possible? Now that might be difficult because that would actually improve the interior point complexity from root n to lower. HMC for non-convex sampling.
So, quick question while the next topic being set up. Yes.
We could use different bases instead of, like, say, P polynomial, but like some polynomial bases, and they're limited to be K, but it doesn't have to be, for example, the low dimensional Fourier. Would you have to know them in advance and then
Right.
or would there be a way that it just needs to be close to any K-dimensional subspace?
Yeah, no, in this, what we've done so far, explicitly used explicit knowledge of the polynomial basis, you know, the functions in the basis to pre-compute their coefficients. You're asking if it happens to be sparse, can you solve it? Yeah, I don't know, that would be very nice, yeah.
Okay, thanks.